everyone to the first ever online industry meeting at Optica, to the first ever networking event for 2 hours, where you're here to find potential partners, suppliers, customers, and maybe even investors. We are going to have 2 hours of very, very strong, of very active networking. I would like to get everyone active. Everyone, open up your screen, share your screen constantly. I want to see you, switch on your camera. It is time to start. Welcome to the online industry meeting in photonics packaging, assembly, and test. Welcome back from your holidays. It's time to do business again. On Monday, August 29th, we are launching the first of a new series of 5 online industry meetings, and we kick off with the hottest topic of all, photonics packaging, assembly, and testing. These meetings are deep dive interactive discussions where we focus on end users' needs in several important market segments, from co-packaged optics in data centers to FMCW LiDAR in automotive. For instance, to address co-packaged and pluggable optics, we'll hear from the major market leaders like Cisco and HG Genuine, both telling us what they need from the photonic industry. And how about LiDAR? You may know that recently, Luminar acquired Freedom Photonics. What does this mean for the new roadmap, and how can the Optica industry network help them develop the right package for FMCW LiDAR? I am delighted that Jan Vardaman can join our discussion to explain what photonics packaging can learn from semicon. She brings us a specialist knowledge from the semicon industry that's essential for hybrid solutions just around the corner. And last but not least, Gordon Killer from DARPA will explain their photonics in the package for extreme scalability program. In our discussion related to opportunities for our members in this DARPA initiative, we will discuss the PIPES project, which has performance goals that will blow your mind. Get ready for a very interactive discussion. Let's get started right now. So, ladies and gentlemen, we are live. We are live, and we are here to find ways to connect. This meeting combines all the entire supply chain. We have companies here who provide packaging solutions, equipment, fiber to chip assembly, silicon photonics, indium phosphide, silicon nitride. The entire supply chain is here, and we are here, the Optica staff, to make sure that you all connect. I started working for Optica already 6 months ago. My job is to make sure that Optica becomes an industry network globally, and all the companies in our network find the most important membership benefit of all: the other members. Our goal is to act as a catalyst and connect them. All of you, many of you are Optica corporate members. Just to remind you, what you get from the Optica membership is access to market reports, access to events, but most important, introductions to those companies that you can do business with. And these events are only your tools to make those introductions. I speak on behalf of 160 Optica staff. In this slide, you can see our Optica Corporate Engagement Council with CEOs of top companies worldwide. These are the people who tell us how to drive this industry network. I would like to also acknowledge our president, Professor Satoshi Kabata, and the rest of the Optica executive staff. Together, we are here to bring the Optica former OSA most renowned academic platform to be the leading industry network to connect companies with potential suppliers, partners, customers, investors, and hireable talent. We organize about 400 events per year. You can find all of them in the website, but I want to just highlight that today we have the first ever online industry meeting at Optica. These meetings are 2 hours in which all of you are part of the meeting. This is not a webinar. You came here just to check your email while you telework. No, this is not the point of this meeting. The point of this meeting is that all of you find ways to help the 5 end users we selected for you. Today, we are addressing the topic of photonics packaging, assembly, and test. Next and last Tuesday of September, it is all about femtosecond and picosecond laser applications. They also remember that many of you are applying for providing industry tutorials. We're going to announce many industry tutorials in the coming months. If as a company, you want to teach how to use your equipment to solve challenges, let us know and we will provide you with a 1 hour online meeting for you to teach the rest of the industry how your equipment can solve an industry challenge. And also remember, we have now online in the Optica industry summits, face-to-face Optica industry summits. We're going to have about 10 per year. In the rest months, we have one in Paris, 26-27 October, to talk about the quantum industry. We're selecting 30 quantum startups, companies in the 5-year business, who are going to tell us how the rest of the supply chain can help them. And on the 8th and 9th of November, in Silicon Valley, many of you are going to be there, co-packaged and pluggable optics. We want to find the entire supply chain of co-packaged and pluggable optics, bringing all together to Silicon Valley, hosted by DuPont Technology Center in San Jose, to find ways to connect. But today it is all about the photonics packaging, assembly, and test. I would like to thank all of you, thank the amazing Optica team that put this together. I really had a big dream for this first meeting, and my expectations were much past. We have 490 registrations, and we have selected 5 companies who are driving the industry and who are here looking for partners, looking for people to help them. We have Peter Develer from Cisco, Gordon Killer from DARPA, Gordon Morrison from Freedom Photonics, now a Luminar company, Jim Theodoros, my friend Jim from HGTech, and last but definitely not least, the very well-known Jan Vardaman. Thank you very much, all of you, but these are or featuring speakers, but all of you today in the Zoom room are part of this meeting. Also, I would like to remind all of you that this meeting is also live streamed in YouTube. So let me say hello to the YouTubers. Hello, YouTubers of the world. If you're following this meeting from YouTube, just make sure that you write all your comments and questions in the chat, and we'll read them during the meeting. For all of you in the Zoom room, remember that you're here to connect. So make sure that you find who else is in the room as well. Everyone in the room, the 125 people already, is going to grow to 400. All of them have shared the company name. Just, you know, what kind of companies are in the room. In the next meetings, I'm going to publish also a supply chain, but for this first ever meeting, there were many companies that I wasn't sure where to position them. I want to talk to them first. That's why this is the first ever meeting, because we're going to have the supply chain with all the companies registered. And that's all I had to say. I want to give the floor to our first featured speaker, a personal friend of mine, Peter Develer. Peter Develer, we know each other for a long time from Europe. Thank you very much for being here from Luxtera, now a Cisco company, telling us how the rest of the Optica supply chain can help you. The floor and the attention of everyone goes to Cisco.
Okay, thank you very much for the introduction. Yeah. Let me bring it. Can you see my presentation correctly?
Crystal clear.
Okay, so let me start here since we have a little time. So I'll give a little overview of what our approach is for packaging, assembly, and test of silicon photonics optical transceivers. And so it's narrowing down the applications a little bit. It's for the use of silicon photonics for optical transceivers. So if you look here at the trends that we see in technology requirements and product requirements, is that bit rates are steadily increasing. Okay? So now we are at 56 gigabyte per second. We are going to 112, and in the future, potentially, we go even to the double of that for both the electrical and the optical interfaces. And that means that not only the optics have to go fast, you need fast modulators, fast photodetectors, and so forth. You also need the electronics going with that. And that means that we will need advanced supporting advanced CMOS nodes. So currently designs are done at 7 nanometers. In a couple of years, or actually maybe now already, we are already working at 5 nanometers, and in the future, 3 nanometer CMOS. Another thing that is very important, and that ties into the packaging, is that the parasitics, the electrical parasitics of resistance, inductance, and capacitance, to a large extent, affect the performance of optical transceivers. So you need very advanced, low parasitic electrical interconnect, and that ties directly into the packaging. Another thing that we see is that, and that is, we just heard that there's also a lot of talk about co-packaged optics. We need higher levels of integration. So we need more channels and more optical IOs per square millimeter. That drives that everything has to be more compact, not only the optics, but also the electronics. You have to connect everything very closely together. What this has as a side effect is that also the power dissipation will get much more concentrated. And that makes that heat sinking is also a challenge. So that's also something that is adding to the packaging. And there again, how these things are solved are by using dense electrical interconnect. So copper pillars, interposers, through substrate vias, and so forth. And also, it also means that the photonic die, the PICs, are getting larger than they are currently. That's also poses some packaging challenges. And finally, of course, there's the manufacturing. We need high volume, low cost manufacturing. I know that in optics, there are many applications where with different kinds of volumes, but for optical transceivers, you have to think about a couple of millions per year in production. So all your design must be for manufacturing and low cost. And you have to be able to ramp to high volume in a pretty short time. So time to market is important. So our approach there is that we want to leverage as much as possible mature technologies, automation, and try to make things as simple as possible. To the right of the slide, you see there one of the things, evolutions that we went through is that we went from wire bonding the photonic chips towards through substrate via or 3D packaging for the silicon photonics. I will show some example in the next slide. So this slide is showing some examples of things that we have done over the years. The first one is that we want to use that packaging technologies from the electronics. So we started with using micro bumps to attach an electronic IC to a photonic IC. And currently, the current products they are using through substrate vias. So 3D packaging. That is basically where we have in the photonic IC, in the PIC, we have drilled holes and fill them up with copper so that we connect the top side and the bottom side. That solves a number of packaging issues, electrical interconnect issues. And you see that the cross section of a product that we have, that's a 400 gigabit DR4 or FR4 optical module, and that is using that 3D packaging. Another element of optical assembly is wafer level packaging and assembly. So you see there a number of examples. The first one is laser diode packaging on a wafer level with automated pick and place tools. We make millions like that a year. And the other one is showing how we then put the light source and electronic die also on a wafer scale on a silicon photonics wafer. Another aspect there is that in automation, you want to do things on wafers or on panels. And there on the bottom, you see how we do panel level attach of the fiber interface. So that is where we attach a fiber array with an MT connector on a silicon photonics chip. And then the last one is you see there how when everything is put together, what you see there is a 400G DR4 optical module with the photonic die, the electronic die, and the light source and the fiber interconnect. You see that the assembly is very simple because of the high level of integration. And that is the product with the TSVs and the copper pillar bump interconnect. That brings me then to my last slide. So that what is our test approach? Also here, the same as for the assembly, we try to leverage commercial equipment for electrical and optical wafer acceptance test at the fab, and also electrical and optical sort at the OSAT. So this is a machine that we developed with Tokyo Electron, and it does optical sort. It measures automatically optical performance of devices on a wafer. Another thing that's related with the testing is that we have a built-in self-test. So in our photonic chip, we integrate both the transmitter and the receiver. And in the electronic die, we also have a bit error rate tester. actually. So we have a PRBS generator and a PRBS checker. And by use of an optical switch, which we have on our photonic chip, we can switch the output of the transmitter to the input of the receiver when we go into the test mode, and we can test the bit error rate. And that allows us to test optically at high speed without the need for high speed probing. So that's a big advantage and a big reduction in cost when you want to build such devices. And then last but not least, I mean, it's use of the common knowledge in manufacturing. It's a known good die approach. So when you have a flow of manufacturing optical transceivers, all the elements you bring in, you know that they are good, and then you assemble them with a good process flow, with process monitoring, and so forth. That allows you then to optimize the yields and also optimize the costs accordingly. And that ends my presentation. I'm open for questions if there are any later on. Thank you.
Thank you very much, Peter, for a great presentation. It is so great to have you here. We have many questions for you because we have the entire supply chain in front of us. But the first thing I would like to tell you is that since I joined Optica, I haven't been stopped traveling, and I went to Austria to visit a company called Besi. Do we have anybody from Besi in the room? Is Peter with us?
I'm here,
Peter's
Jose. Yeah.
Hey, Peter, it's good to see you. As you have seen in the previous slide, we saw from Besi. Sorry, we saw from Cisco their need for wafer and panel level assembly, leveraging passive and active alignment. When it comes to the passive and active optical alignment, that's something that we're going to discuss later, and we have companies in the room like Ficontech, for example. But I would like to understand what does Besi do from the equipment perspective, and how you could support, how you could contribute to this wafer level assembly that is needed for the next generation optical assembly.
Yeah, thanks for asking, Jose. Actually, we're in the passive alignment market, so we do not do active alignment, but of course, with our very flexible platforms at Besi, we do passive alignment. And mainly we are delivering to direct attach die attach equipment or also flip chip equipment. And if I look at those processes we're looking at, there's also one very new and interesting platform that we have been working on in the past 3 years, where we do a so-called direct bonding process. So it's a real covalent bonding process where there is no flux, there is no epoxy or neither a bonding agent involved. It's basically bringing quite high quality, let's say, surfaces together and initiate bonding via atomic forces. So that could be one very interesting perspective for the maybe not the so near future, but further future. And we have a platform that's actually really doing this already now, and doing this already in serial production for one very specific product.
Yeah.
Peter, in all the meetings that we had so far, we always discuss on how annoying is epoxy. Could you let us know, I'm sorry that I interrupted you, Peter, how this glueless, epoxyless bonding could be a solution? Peter. No, Peter, I mean, Peter the Doubler.
Sorry.
Okay. I think that the technology that was just mentioned is indeed very interesting. Not so much because it does not use epoxy, but just because it allows direct bonding of an electronic die to a photonic die. And what's important there, what I mentioned in my first slide, is that can be done with minimum parasitic capacitance. And that is very important for the high-speed applications. When we go to beyond 100 gigabit per second, having these direct bonds of two dies to each other without a solder connection is very important for reducing the parasitics. And that's indeed a very interesting field to look into.
I don't know, Peter, if you have with us one slide that you could show us about the direct bonding done at Bessie, because I really, Peter, I have a problem when I have two Peters, Peter and Tel Baditzer.
Yes. If you allow me to share my screen, if that's okay
Always.
with you.
As an Optica member, you can always share one slide at all our online industry meetings.
Okay, basically I prepared for this meeting 4 slides that I would like to present to you. It's really very basic and no technical slides in this, just to give you an idea what we are doing with this platform. That's okay with you. Sorry, presentation mode. Can you all see my screen?
Crystal clear.
So direct bonding, I do not know whether you guys are all aware of that, but in principle is this something if the components and their surfaces are sufficiently smooth and flat, a bond front will propagate outward from the first point of initial contact. That's a process well known, like EVG has done that on wafer to wafer level. And what we are doing is we're doing this on a die to wafer level. So meaning bringing those two parts together, and by simply at room temperature applying a very low force, bonding is initiated. It needs an annealing step afterwards to really finalize the bonding. But what you can see in this video is basically just this done by two transparent surfaces. By initiating a little bit force in the middle, it actually propagates the whole bonding wave throughout the whole wafer. And what BESI does in this case is doing this on a die to wafer level, meaning in our machine we do have a source wafer or a source carrier of dies, for example, can be a framed wafer with our already diced dies, and then we flip chip bond this onto a target wafer. Of course, there is a lot more involved. Those wafers and all parts involved need prior treatment, activation, cleaning and activation, plasma treatment. And once we have done this, there is another step, an annealing step, where actually the difference in thermal expansion between the silicon and the metal, let's say the copper, will lead to those two copper parts really making contact and making a bond itself. So there is no agent or no epoxy or nothing else involved. We have very high quality interconnect silicon oxide to silicon oxide, as well as copper to copper. And I think both is quite important on the silicon photonics world, because on the electronics you want best possible coupling, but also on the optical side you do want to have minimize the losses when you're trying to couple in light from actives or a laser source. And yeah, that's just the advantages I do see with this technology involved. There is no flux. Also quite important in our case is high accuracy. We can go down to 200 nanometers of alignment accuracy, 3 sigma. It's a very clean platform, down to ISO 3 even in the bonding area. We can do room temperature bonding. Also annealing is at moderate temperatures, around 350 to 400 degrees Celsius in the end. And I do assume that with this technology, also in the silicon photonics world or in the PIC world, you will get high optical and electrical connection quality. And of course, what's very important, it's not only from a technical perspective, but also with our bonding equipment, which is a dual gantry flip chip equipment. You can get to UPH of up to 2000 for these accuracies. That's what we're working on right now.
Thank you very much, Peter. You have been the first one slider for the online industry meetings. Remember when I say one slide,
sorry.
Peter, please. But we have questions for you. The first one is coming from SAIS in Jena. Ulrike Boeing is with us from SAIS, the leading manufacturer of optics and optical instrumentation. Ulrike, good afternoon.
Thanks for organizing. This is actually quite fantastic. So no, my only question is actually about the if you could maybe specify a bit more what the losses are approximately for these bonding steps, because right now you said that it's quite supreme, it's quite nice, but could you just provide us with some numbers if possible as well? That would be great. And I'm in Oberkochen, by the way, not in Vienna.
Ah,
sorry.
okay.
But anyway.
But losses, you mean in terms of yield, right?
Yeah.
Okay, I'm not sure. I'm not the project manager for this platform, and I'm not the process expert. I do assume we can have a yield up to maybe 80% right now. It's a quite tricky process. Of course, we are targeting a lot higher yields, but that's not only up to us in this case, because for example, the source wafer, it's a diced wafer, and it's a wafer that's framed. So you have a tape, and then you have a standard ejection process. So this usually introduces particles. When you eject this wafer, you then pick it up, flip it, and flip chip bond it onto the target wafer. So there is a bit of yield loss involved, since you will generate some particles, and as you might know, even a quite small particle between those surfaces will corrupt the interconnection at some point. We have a working process that is currently running at a quite big customer from our side, and frankly speaking, I don't know how good the yield is at this stage. There is an official product available already now that's produced with this machine, but I'm not even sure if we even have those yield numbers.
Danke, Peter, and danke, Ulrike. I go from Peter Utterwalitzer back to Peter the Doubler. Peter the Doubler, there's a question from you coming from Photonics IX, and I'm going to try. Is Sushant Kumar with us today?
Oh, yep, I'm here.
Please tell us what's on your mind.
Oh, yeah. So thank you very much for organizing this. It's really great. So I just wanted to ask, when you're connecting fiber arrays to chips, does that pose any issues in terms of the uniformity of the fiber array and the presence of, or maybe the need for the groove block on the fiber array side itself, in addition to whatever passive alignment you need to do on the chip side? And if that has any issue, any implications with regards to performance or cost or something like that?
Yeah, sure. We use glass V-groove arrays with fibers in them to attach to the photonic chip. Usually, the manufacturers of those fiber arrays can make them with a core tolerance is less than 1 micron, and that is sufficient for us. Because we use grating couplers to couple light out of our silicon photonics. So that is a mode size which is very similar to that of a standard single mode fiber. So there is we can allow some misalignment. A micron misalignment is not really affecting insertion loss to a large extent. On the other hand, what is important is if you attach fibers to a TSV chip, TSV chips are usually thinned down to about 100 microns. Usually they are not completely flat. So if you have edge coupling, the warpage of that pick may misalign with respect to the pretty uniform alignment of the fibers in the V groove. So warpage of the silicon photonics thinned pick may be a challenge when you do edge coupling. Yeah.
Thank you.
Peter the Doubler, I would like to address quickly with you the topic of testing. We have here, you have told us a bit about the testing approach for silicon photonics. Is there already a standard probe to do the wafer level testing of silicon photonics?
Well, we have, as I mentioned in my presentation, Tokyo Electron we have collaborated with Tokyo Electron in Japan to build an optical prober based on their standard probing systems. The difference is that the electrical probe card is replaced with a fiber array, and there is software running on the machine that is doing the active alignment of the fibers during the test. So that is one platform, and I believe there are some other ones in the market as well. that offer commercial optical sort capability.
Yes, there are. Actually, Tobias Nausch from Genoptic. Good afternoon, Tobias.
Good afternoon. Hello, Jose. Thank you for having me here. I had actually one comment on Jose's announcement, and so we, for me in Optic, we do have a kind of standard probe for measuring optical and electrical peaks in parallel and with standard equipment. So that's called our UFO probe. And on the contrast to the active alignment, we go the path for passive alignment so that it runs really on standard equipment. So Tokyo Electron Prober, Accutrack Prober, and we are also going to make it compatible to the tester approach that you can use it with high throughput testers. And my second thing was also related to that, the question to you showed that there is an BIST built-in self-test in your devices, and I was wondering if there's really a built-in self-test, how big is the need for actual wafer level test, optical and electrical?
Well, the test strategy has many steps. So there's when you have the photonic wafers manufactured, there's a wafer acceptance test at the foundry. So there they test structures in the scribe grid, and they are both electrical and optical. So that is done with a prober that I just showed a picture of. Mm-hmm. We have consigned to our foundry. And then when that is done, you do optical sort, and during optical sort, you test every chip that is on the wafer optically. And then you have, depending on which flow you have with TSVs or without TSVs, you have then also a test when the electronic chip is attached to the photonic die, and when the light source is attached to the photonic die. And when you have all three of them combined, you can contact the whole chipset assembly and have the whole thing operate. You can switch the light source on, you can switch the electronic IC on. The electronic IC can drive the modulators, receive photocurrent from the photodiodes. And so you can make a whole loop, having the light source on, modulate the light with a bit pattern, then you can receive the bit optical bit pattern, and then we have in our electronic die like the bit error rate tester with the error checker. So you compare with what you send out with what you receive, and from that you can determine the bit error rate. And at the same time you can turn the light source down as you do that, and you see then how sensitive when at which laser power your bit errors start to kick in. And so that gives you a quality of your transmitter and your receiver link. And that's a very low cost because you don't need high speed interconnect to that. Everything is all the high speed is contained on the chipset. Okay. So it also tests the light source, so you test the whole thing.
Peter, we have many people who want to ask you questions. Remember that there are many important companies that want to work with you. We have, for example, Femtoprint in the micro-optics domain. We have companies like Freedom Photonics, like EVG, everyone here that you want to do something for them. Post in the chat your room for cooperation and use the chat to interact with each other as much as possible. But I want to give the floor to a very close, very dear friend of mine, Mark Lukovic from 5 Reality. Thank you very much for supporting me in this new job. What's on your mind? Mark, you are muted.
So sorry about that. A question for Peter at Cisco. I seem to remember some advertising. My memory is as good as it used to be. Of some advertising on you having a discussion about CPO, and I can't remember your title slide. But I thought I'd get you to talk about CPO and OSFP XD. What's the current thinking at Cisco right now?
We believe that pluggable modules will always be there if the electrical connections work, and especially you might have heard the discussions on 200 gigabit per lambda. If the electrical interfaces work, a pluggable module like the OSFP XD is definitely, if you can get that to work, will be used for sure. Co-packaged optics is way more specialized. It is very interesting. It potentially allows you to reduce the power dissipation, because that's what it's all about. If the power doesn't go down compared with pluggable modules, co-packaged optics makes no sense. So, but co-packaged optics is much more specialized, and it is not as universal as a pluggable module. But that's an interesting point, because the power needs to go down, and as the terabits per Ethernet switch are increasing, we're really hitting issues there with pluggable modules.
Before we go to the next speaker, for you, Peter de Develer, and also from you, Peter Andervaditzer from BESI, there is a question from Siena, Jean-Frédéric Gagne. Jean-Frédéric, thank you very much for being with us today. What's on your mind? Jean-Frédéric Gagne, could you please unmute your microphone and tell us what's on your mind? I will read his question because he texted it to me. He said, how small can two electrical contacts be aligned from the die to wafer accounting for all sorts of errors? So how close can two electrical contacts be aligned? Peter de Develer.
Oh, I think this is a question for
Peter Andervaditzer.
Because he makes the machine that can align it. So,
I mean, we make the machine that can align it, and it then depends also on our customers that supply the material that we do need to bond together. What I can tell you is that our machine can, with quite good material, can reach alignment accuracies of even below 200 nanometers, 3 sigma. And that's taken into account die sizes of up to 20 by 20 millimeters. So even at the corners, we can reach this. So over the whole die surface area, we can reach around 200 nanometers, 3 sigma.
Yeah.
Peter, Jean-Frédéric is now with us. So Jean-Frédéric, did I voice your question properly? Maybe you want to ask yourself.
Yes, very well, and that answers. So no worries for electrical contacts for high speeds, for example. Thank you.
Mm-hmm.
Peter de Develer, Peter Andervaditzer, companies like Zeiss, like Genoptic. Thank you very much for this first Q&A of the first online industry meeting. We're going to continue now with the next speaker, but what a way to start. We continue now. We continue to the next topic in the agenda. We want to understand how to assist from this global industry network, how to assist the DARPA initiative when it comes to photonics packaging and test. And we couldn't find anyone better, because there is not, than Gordon Killer. Tom Hausken, a very dear person, all of you know, found Gordon Killer and pushed him here to be the voice and to help us connect. Gordon, thank you very much for being with us today. The floor and the attention of everyone goes to DARPA.
Great. Good morning, good evening, wherever you are. Hi, everybody. Thanks for joining. Let me share my screen. Share. All right. Okay, so trying to stick to Tom's recommendation of going with only, hold on, let me go. Only 6 minutes. I couldn't only do one slide, but I thought I'd kind of share the perspective of DARPA here. We have a number of programs in optical microsystems, which is all about packaging things very small, very accurately. And we do a lot of work on sort of wafer scale photonics, but ultimately you need to put a lot more in the package. Just a reminder, DARPA is a US government agency that's really charged with doing a lot of development of innovation. We've been around for quite some time and been working in microelectronics and a lot of system level things like GPS and autonomous navigation and AI machine learning. But I'm going to talk just about integrated photonics and optical microsystems. I think today we're going to hear a whole lot about co-packaged optics. And there's obviously other things that are coming on board in terms of digital compute. There's optical interconnect, sure, and as optics moves closer to the package, closer to the XPU, we need better packaging. But there's also concepts like optical accelerators, where we might be able to put photonics in the package and maybe not use fibers at all. That would be very exciting and maybe drive volumes much higher than they are today. Another direction we're going is what I kind of call optical front end. This is using photonics for things like ranging, like LiDAR, imaging, using it for laser comm and free space optical communications, obviously fiber comm as well, optical displays, and AR, VR. And optical packaging here actually has a lot of similarities with some of the other stuff happening in compute. Third quadrant that I show you here is microsensors. At DARPA, we in particular have a lot of work going on in the areas of positioning and navigation and timing. So very sort of small chip scale clocks, magnetometers, gyros, accelerometers, and also doing chem and biosensing. And while we might be worried about very precise sensors, a lot of this, as a lot of the reduction in size, is very applicable to wearables, which is another huge market for photonics that I think is going to be exploding pretty soon. And then finally, I lump a lot of things here into this emerging compute, where we're doing things in analog domain, signal processing, microwave generation, and a lot of quantum systems, quantum information processing, and quantum sensors. I thought I would, without digging real deep into this, just kind of give you a highlight of my day. I get to work on many different programs with a huge number of fantastic technical groups, many of which I actually saw online today. The PIPES program is one of our big investments in essentially co-packaged optics. I could talk your ear off about this, but we're seeing a lot of the same challenges here, looking at 2.5D and 3D electronic photonic packaging, fiber attach, high quality laser development, comb lasers. The CHIPS program is a 2.5 and 3D integration program, helping to drive chiplets, which may be digital, maybe RF, maybe optical as well. The LUMOS program is about bringing different photonics together, and this is essentially enabling the world of heterogeneous photonics. And I could talk about this quite a bit. We are seeing teams doing microtransfer printing, doing heterogeneous laser integration, hybrid laser integration. Maybe the most important or interesting that's, I think, going to change the industry is heteroepitaxy. And I noticed we've got some folks from SUNY and AIM Photonics here, and they've been working at, with some of their partners, growing 3.5 quantum dot lasers on 300 millimeter silicon and integrating thousands of devices per reticle in a full CMOS fab. And that's really exciting. It gets rid of some of the packaging challenges, actually. MOAB is a LiDAR program, chip scale phased arrays for non-mechanical beam steering. Griffin is about RF, very, very quiet microwave oscillators based on photonics. Again, an application where you might have photonics inside the package with no fibers to or from. And photonics is an enabler, which goes beyond what you can do today. And then DODOS, which is about optical frequency synthesizers on a chip. It really pushes combs. So I think the last slide, I wanted to, without pointing out any one particular team or technology, just kind of give you a sense of the different types of packaging that we're seeing. Under pipes, there's a lot of co-packaged optics where, again, there's 2.5 and 3D microelectronic integration. Power is a very big driver here. We're going to 1 picojoule per bit, including all the electronics, which means you have to push it very close to the electronics. Many, many fibers. In some cases, we've seen teams that have 15,000 bumps per pick, teams that have more than 100 fibers attached to a single chiplet. We're seeing integration, 3D integration with digital, analog, and photonics all together in the same package. Again, I mentioned all the different ways people are attaching lasers, modulators, and so on to different materials. This might be silicon, silicon nitride, thin film lithium niobate. MOAB program is a kind of a nice shot of a full reticle size pick that has, in fact, many tens of thousands of components on it. It has many different ASICs attached to it, which again, there's thousands of bumps per ASIC. And then light comes off of this chip and steers in free space in 2 dimensions to do FMCW LiDAR. Griffin, we're seeing a lot of work with stabilized microcavities for ultra narrow line width. In particular, some results that are getting us lasers that are sub-hertz line width using semiconductor lasers. And then finally, Dodos is kind of a tour de force in complexity where there's tunable lasers, narrow line width lasers that are pumping silica wedge resonators, silicon nitride resonators, nonlinear photonics to do frequency conversion, and then high-speed electronics all in the same package. So essentially, I guess what I'd like to say is there's a whole lot of photonics packaging that needs to come about to enable all of this. And so we at DARPA have a new initiative. This was just announced a couple weeks ago, and it is called NGMM, Next Generation Microelectronics Manufacturing. This is a solicitation to the community. All of you folks should have a look if you think you can weigh in. And we are looking for innovation in advanced packaging. We have investment money set aside to do this. We don't have as specific goals as sometimes we do because we're trying to do a phase 0 and get a roundtable going where there are a number of voices that are willing to weigh in. What we'd like to do is help to stand up a national facility to do early prototyping and bring some of these needs together. How do you do 3D fine pitch packaging? How do you bring photonics and MEMS and RF to this? And how do you develop some of the new packaging technologies to do prototyping? Anyway, NGNM, it is out there. I think the proposals are due on September 21st. With that, let me stop and pass it back to Jose.
Thank you very much for a great presentation. It means a lot for us to have DARPA announcing new initiatives and room for cooperation, because this is what it's all about. Gordon, I have a difficult question for you, but I have to ask because I represent a global yes. industry network, and you presented a national initiative. Is there room for companies outside United States, and how you can help me connect the industry globally?
Yeah, it's a great question, Jose. So I actually work very closely with many of the folks online here who are not from North America. It becomes always a bit of a delicate balance because DARPA is funded through the US, through tax dollars. And so it tends to be a preference to build up capability domestically. However, everybody acknowledges that it's a global marketplace and global innovation is important to embrace and to pursue. And so, wherever possible, we like to work with all partners. And typically when we have a solicitation, it's made clear what we're allowed to do within that one. And so this NGMM is not my program, but I think it's spelled out in that to see who's allowed to participate.
There are many people with questions and room for cooperation in the room. I'm gonna bring you first to something that we're gonna push from Optica in the coming years, which is the micro-optics revolution. We believe that many companies are really making a big push for having different wafer level optics manufacturing from different processes, and that's about to revolutionize the industry. I'm gonna present you to one company that maybe you haven't heard from, but they are becoming and growing really fast. The company is Photonics, and the person is my very dear friend, Rolando Ferrini. Rolando, thank you very much for being with us. It means the world to me that you're here on the first online industry meeting. I would like if you could tell us quickly what Photonics does, what is the manufacturing process for micro-optics of Photonics, and how you can address the packaging of maybe these sensors that they were put on the table from DARPA.
Thank you, Jose. It's a pleasure to be here. So Photonics, we have a technology platform, and we do 3D printing, or better, writing into glass. So we micro manufacture glass components that combine several functions. We have heard a lot about co-packaging. We heard a lot about miniaturization and combination of several functions. So what we can do at Photonics, we can micro shape the bulk of the glass in three dimensions and produce micro optical components or systems. This can be a combination of micro optics, micro lenses, micro mirrors, but we can combine also with interesting features. We have heard about V grooves. We can combine these micro optical elements with V grooves, but also with 2D ferrules for fiber arrays with a precision that goes below 1 micron. We are today at the precision in diameters and positioning of these holes of about 0.5 micron, which is compatible with what we heard a few minutes ago. We can combine with waveguides that we can write in 3 dimensions into glass. So we can offer really a full solution combining several functionalities monolithically in one single component, going up to micromechanical features that could be added. So this is the entire set that can be put into a component, a glass component that can be actually welded or combined or packaged with the optoelectronics components we're talking about. And we can produce this chip by chip, but also at wafer scale. We routinely work today at 8 inches already.
Rolando, as you have seen in the presentation from Gordon, he spoke about the MOAB initiative that is looking for a free space coupling into a photonic integrated circuit already packaged on a CMOS integrated chip. That's something that you have been looking at, is that there are micro optics for doing the free coupling between remote light source and the photonic integrated circuit?
What I can tell you is that today we're working a lot, and these are requests from customers in solutions for coupling, let's say, fibers or fibers arrays with PICs, with photonic integrated circuits, and let's say tackling the two approaches coming from above and then turning the light at 90 degrees, or coming from the edge and coupling directly into the optical chips. There are several solutions, and these are requests that we are tackling and then trying with the customers to solve today with our technology.
Gordon, when it comes to these MOAB free space coupling challenges, could you share with us a few more details about the key challenge for the free space coupling into that photonic integrated circuit?
Yeah, sure. So as you scale up these arrays, you might want to do higher and higher power. And so coupling a widely tunable narrow line with chirpable laser into this system was first done with fibers. We're now doing on-chip gain, on-chip lasers, on-chip amplification to get rid of a lot of that free space coupling. But I would say that you bring up a really good segue, I think, that often we're talking about how do you couple from a PIC to a fiber. But what we're seeing in our microsystem programs is that you need to very efficiently couple into many different things, into free space, couple to micro cavities, couple to atomic vapor cells, couple to trapped atoms, and micro optics, especially 3D additive manufacturing types of approaches are really compelling to do a lot of these different things, I would say.
Another topic that I wanted to address with you, Gordon, because there are many Optica corporate members that can help here, is the topic of co-packaged optics. We are going to have many different meetings, and I hereby invite you to our event in Silicon Valley next month of October. But one thing that we really see from the co-packaged optics approach is the need for new connector with very high level of integration. So from Optica, we started scouting technologies that could help the aligning of a large amount of fibers. And we found out one company that was not very well known by many of you. The company is called MicroAlign. And I have somebody here from MicroAlign. The person is Dario Locascio. Dario, good afternoon. I believe you're also in the Netherlands. Good afternoon. Can you tell us a bit of MicroAlign and how could you help the challenge from DARPA on the co-packaged optics, especially on those high-level integration of many fibers?
Yeah, thank you, Jose. And indeed, I'm in the Netherlands. So I have one slide. I'm not sure how I share that.
Bottom of the Zoom window, there's a green arrow up that says share screen. Click on it, and then it's very important. Select the window you want to share with the world.
This one. So you probably can see the slide now.
Crystal clear.
Okay, what we have done is we developed a reconfigurable V-groove in order to align not the claddings of the fibers, but the cores. So this way, the pitch of the cores is 125 in the end. Currently, we're not there yet. And you can move each fiber individually at the same time. And what the idea behind this is that you solve the difference between coupling efficiency between the different channels. Probably most usable for sensing applications. So actually what we're looking for now is the most suitable market or application for further developing this product. So maybe Gordon can help us in defining what area we should look there.
Gordon, you can see they have an idea to have a very high level alignment of each fiber individually into an array. And that can be used by any kind of sensor or any kind of photonic chip that has many fiber input outputs. Can you think about an application perhaps related to quantum technologies or perhaps related to co-packaged optics that could be benefited by this?
Sure. So yeah, I will say that yes, we see a lot of folks that are having challenges using sort of passive or even active alignment of arrays where you might be only looking at coupling of, say, the two end fibers, and what you get in the middle is not nearly as good as what you need. So this definitely fills a need for certain applications where insertion loss is highly important, I'd say.
MicroAlign is looking for partners. Thank you very much, MicroAlign, for being a corporate member of Optica, like many of you are. One thing that I would like to ask you before we go to the next presentation, it is about what you put here in your slide related to ultra narrow line widths. Let me just share your slide again. You talk about ultra narrow line widths and micro cavities. Do you have some kind of challenges, specifications? In the pipes project, you share with us the specs. Is there any challenges, any dream specifications about the ultra narrow line width for a given laser at a given wavelength?
Well, what I can tell you about Griffin actually is that we're using optical frequency division techniques to create very, very narrow line width microwave sources, right? And so we all use oscillators every day, right? They're in your phone, they're in your computer, but the really high precision oscillators are used in communications, like in a 5G cell tower, and they're used in radar systems and other kinds of, imaging radar, maybe in an autonomous vehicle. It turns out with optical frequency division, you can make the very best microwave oscillators on the planet, better than you can use using traditional techniques. Griffin is trying to use some of these advances in really quiet lasers on chip, and then divide that narrow line width down to sort of gigahertz ranges so that you've got very, very quiet microwave sources. I think this is a underappreciated but really compelling approach for photonics, because you could see it in every base station in a few years, I think.
Gordon, there is a person that I want you to meet regarding this microwave generation technologies, and this person is Guillermo Carpintero from the Universidad Carlos III de Madrid, but very soon from, I don't know if I can say, from a startup, I'll say it anyway, coming on the topic. When you see the Griffin initiative, Guillermo, can you tell us what you do and what kind of room for cooperation brings to your mind?
We are actually working on developing photonic integrated circuits for millimeter terahertz wave generation. And actually, we have worked with ultra narrow linewidth lasers. We are collaborating with Lyonics in that part because they have very high Q resonators in silicon nitride, which make a very narrow linewidth lasers. And what we are actually working is that still, when you have a very narrow linewidth laser, you still have to control the drift between the two lasers. And we are evaluating how that plays off when you have integrated the sources on a single chip compared to different sources actually with different gain materials. Because actually when you do hybrid integration, you can choose even if you have the same gain material and you have the same passive substrate, or you combine all the gain chips in a single indium phosphide chip. And on top of that, once we generate a high frequency, the problem is how to extract the high frequency from the semiconductor, because usually prefers to stay in a high refractive index material. And we are actually working as well in the connectors that will allow us to extract the high frequency from the chips out into connectors that actually have low losses, because the problem is that in optics, we work in microwave photonics because optics is a low loss waveguide for high frequency, but as soon as you convert it back into electrical, you always hit the wall that you have low high losses in coplanar waveguides. And that's the problems that we are working on. Thank you, Jose, for the opportunity.
And thank you, Guillermo, for starting that company. And in one of our upcoming meetings, we would like to hear more, because I have really high hopes for this thing that you are doing. Gordon, you should know that Guillermo has been one of the leading people in the microwave photonics push that we had from Europe, and it is great to have his support here at Optica. Gordon, many people are going to contact you offline because there are things that they shouldn't say publicly, is what they are telling me. So we're going to move on to the next speaker, but please, Gordon, stay with us because the next topic is very interesting for you. Everyone, when we announced that we were going to have a meeting on photonics packaging, many of you told us you need to bring LiDAR, and if possible, you need to bring Luminar to the table. We did our best. We contacted Luminar, contacted Jason, we talked to them, and they told us, if we're going to talk about photonics packaging, you need to put Freedom Photonics on the table, our latest acquisition, to tell us what they're going to do for packaging, but also tell us how others can help them do it better. So we brought Gordon Morrison from Freedom Photonics, a Luminar company, to the room. Gordon, thank you. Thank you so much for being with us today. The floor and the attention of everyone goes to the packaging of FNCW LiDAR. The floor is yours.
Okay, well, thank you for that enthusiastic introduction. I've really appreciated your energy in hosting this. Let me just pull up my slides here.
Bottom of the Zoom window, green arrow up, share screen, and then you select the window that you want to share. You go to slideshow mode, presentation mode.
Yeah. There we go.
Perfect.
Okay. So, my name is Gordon Morrison. I'm Vice President of Engineering at Freedom Photonics. And as was mentioned, we were acquired by Luminar about 5 months ago. We are a manufacturer of photonic integrated circuits. So we've been doing that for a good 15 or more than 15 years now, and diode lasers, PICs, photo detectors, For applications that include LiDAR, but also quantum sensing, remote sensing, and LiDAR, of course, and also telecom applications. So we've been working in all those fields and have been dealing with packaging problems that, frankly, I think are common quite often between all those different application areas. Now, of course, one of our heaviest focus is in the LiDAR space. So with that in mind, I've kind of put together a slide focusing on LiDAR because, as I mentioned, many of the problems in remote sensing and in quantum sensing, in telecom, they're the same problems in LiDAR, but actually I would say LiDAR pulls all of those problems into one place. It makes it a very complex problem. So what are the things that go into a LiDAR transceiver, which is sending out the light and receiving it as well? Well, you've got a laser chip on carrier of some kind. Maybe the chip goes directly on silicon, maybe it doesn't, but you've got this laser chip that has to be connected to the outside world, both thermally and electrically. We need extreme cleanliness here too. These lasers are not your standard telecom diode laser putting out a few milliwatts of optical power. We're talking watts of power. And as such, if there's any contamination anywhere, you can run into reliability issues much more easily if there isn't really good cleanliness. We've got high dynamic range necessary here. So, if you're looking at a stop sign real close to your transceiver, it's putting in a whole lot of power. Whereas if you're looking at a black dog 300 meters away on a road, you're talking about a lot less photons. And if you're using the same unit, you have to be really clever to make sure that when you're looking at the black dog, you can see it. And when you're looking at the nearby stop sign, you're not blowing a hole and leaving a crater where your photodiodes used to be. We also need to integrate with electronics, as many people have already alluded to. This is a common problem to many other areas, but in our case, we need to avoid parasitic inductance and capacitance when we're pulsing that laser with high powers. Laser trimming of passive components to get the signals just right is not a cost-effective solution. So we've got our own ASIC design house, of course. Black Forest was also acquired by Luminar, and we're working together to integrate all that into one tiny little package. Optical coupling, of course, is also a problem. There's optical coupling to fiber involved. There's optical coupling to free space, of course, involved. And all those alignments are really critical. And for all sorts of LiDAR companies, and different companies have different approaches, of course, there is a fundamental problem of how do you get light out of a tiny little laser diode where you're talking about a 1 micron kind of diameter waveguide, hit something 300 meters away and then couple it back into a very small space, possibly another waveguide. We've got micromechanical type stuff. In our case, we're using rotating mirrors, but there's other approaches as well. So there's a lot of vibration considerations in there as well that come to mind. And then finally, there's the thermal management of all this. The environment you're working in is brutal. You're talking about way below zero freezing temperatures and going up near the boiling water temperatures as well. And you've got this high power laser that has to perform across all those temperatures. So if there's anybody out there who can make a better tech than what's available right now, I'd love to hear about it. But we're doing everything we can with existing technology to optimize and minimize power consumption, of course. And these problems that I'm listing here, I would argue are common in all cases to at least one example of atomic sensing, of remote sensing, and in telecom, which are all areas that we've been playing in. Another area that's kind of come up, we found over time is that's a problem, and which we've made our best attempt to find a solution for is reliability testing. The world of technology, as you're all aware, is one that moves really fast. You can't go perfecting a complex system and then afterwards start reliability testing for a year to see whether or not it truly works or if it's going to fail for some reason. So generally we have to be kind of building the airplane while it's in the air a little bit here. So we need to get reliability testing started on chips that may not actually be the final product. It may not have quite the right number of contacts. It may have a slightly different power consumption. And how do you do that without building a new rack every single time? There are services out there where you can get chip-on-carrier lasers measured, but we're talking about photonic integrated circuits that have many, many contacts. They've got modulators, they've got SOAs, shutters, high power components, tunable components, and every single one is different. So what we've done, at least for preliminary reliability tests, we've had to build our own racks that are very, very, very reconfigurable, allowing us to introduce a wide array of multiple current sources to any one component. So each of these racks will do 60 different parts and allows us to test modulators, shutters, photodiodes, high power, low power lasers, and has automated testing built in. That way, when we've designed a chip, even before we've completed the wheel between design, test, prototyping, and back into redesign, we've already got these things running through reliability to make sure there's no gotchas in advance. I think that sort of thing is really useful, and I hope that services like this will become more common in the future, because it certainly is a requirement that we have. Another area that we've got in our back pocket that I think some people will find interesting is photonic wire bonding. We have a tool from Vanguard where we built our own, high-end clean room for environmental control within our Class 10K manufacturing packaging clean room. This is a method we use for connecting chips to chips and chips to fiber. In particular, with complex problems where we have either silicon photonics chips or PLCs, passive light wave circuits, with multiple ports needing, say, an array of lasers, an array of tunable lasers, an array of DFB lasers, sometimes more than one array of DFB lasers, for instance. That sort of packaging problem is not easy to solve. We've done it before with mechanical, piezoelectric 6-axis tools where it's a very boutique approach. But when you start talking about 16, 18, 24 lasers all in a row, with all the bending and the different thicknesses of the chip itself varying, and you need kind of sub-micron alignment, it becomes almost impossible to do that. With this system, you can package things up and have 10 microns of slop here and there, no problem. It's very easy for us to do with our existing manufacturing tools. You come in afterwards and use the high resolution camera and optics to locate the waveguides, and you just write your waveguide from point A to point B. Moreover, you are also able to mode match. So instead of designing your DFB laser to be not the best in class DFB laser, but to be a good DFB laser with a spot size converter, and instead of having to put all kinds of complex spot size converters on your PLC or photonic chip, you can in fact match the waveguide to each of those and adiabatically taper across to the next one, and you end up with a nice reproducible optical coupling between multiple ports on two chips. So this is a new technology. It'll be interesting to see where it goes. We're using it for prototyping right now. I'm certain and confident that it will become very useful for high-end, low to mid-volume products. And I'm interested to see where over the next few years it will go for high volume products. So this is another area that we're working hard on developing at Freedom Photonics. The last slide I've got, I won't bother reading through. It's basically a summary of the information I already talked about, but common problems across application areas that we're involved in include hybrid integration, the coupling of light to and from different waveguides and into free space, combining and demuxing light sources within a package. Of course, the thermal power management problems, co-packaging, compact, control electronics, and calibration electronics. All these different areas require that. And of course, then the reliability of these complex packages afterwards. And all of that, and this is the last point I want to make, needs to be done at high volume and low cost. With automated assembly test. Visual inspection is really important, pass-fail criteria throughout, and full traceability of that. So that's my 2 cents on packaging for optoelectronics.
Oh, thank you so much. I mean, when we asked you to come, we never thought that you would really share with us all the key room for cooperation with the other Optica members. You really understood what this meeting was about. And there are many people who can help you here. There are many people who can help you. And I would like to see, first of all, to ask now everyone, you see there are common problems that they have, to ask everyone who have a way to help Freedom Photonics to tell us right now so we can start the discussion. And I'm going to start by going to France. I'm going to France to a company called Icon Photonics. Jean-Luc Polos, are you with us?
Hi, everybody.
Hi, Jean-Luc. So you
Hi,
see that
Jose.
they are looking for a potential solution for the coupling of light to and from waveguides. We had discussed in the past the micro-optics approach that you have with the MEMS for the coupling of the fiber to the chip. And you can see how they are not a stranger to micro-optics because they already use two-photon polymerization. So could you tell us what Icon Photonics does and how you could help, particularly Freedom Photonics today?
Yes, thanks. Thanks a lot for making the connection about that topic. At Icon Photonics, we're working on optical waveguides that we manufacture on top of the optoelectronic chip, photodiodes, the lasers, VXS for top illumination, but also we can connect with PICs on the edge. And it's, as opposed to the two-photon polarization, it's in a one-step lithography that we fabricate this 3D structure, which is a tapered waveguide. And the advantage of that process is really to make it at the wafer level, full wafer level, with low cost. And at the same time, with the tapered waveguide, you can ensure very low loss. Obviously, you don't have the same flexibility as a two-photon polarization that is really suitable for prototyping, for very fancy structure. But when you have a simple and straight objective that could lead to very low loss, because we can have less than 0.5 dB coupling losses in some cases, with multi-mode fiber or single mode or multi-core fibers.
I think, I don't know if I'm going to ask too much, but Jean-Luc, do you really have one slide that you could share with us to make it more visible? Otherwise,
Sure.
I'm going to give you a few minutes so you to share one slide. And in the meantime, Gordon, I'm going to go to a company which I believe already you know. I'm going to go to Darrell Port from Aerotech. Darrell, what's on your mind?
Yes, I just wanted to quickly introduce myself to the group and just listening to some of the challenges that are mentioned in these presentations, it just really hits a lot of spots with what we work with customers each day. And so just a couple here. One that I saw last week was a customer that was working with landing fibers into a V groove and making sure that as those individual fibers went into that V groove, that there was not any skewing of that fiber, the fact that it stayed straight and that you were getting optimal signal into each one of those channels all at the same time. And it is a challenging application, but it is something that we work with customers on. And then just lastly, in terms of the challenges that Freedom Photonics was bringing up in terms of getting that ultra high resolution of alignment, and they were working with, piezo stages and how sometimes it's, in his words, a boutique solution, both from a performance standpoint and a reliability standpoint. We've been able to get those levels of alignment within using a linear servo stage technology in all 6 degrees of freedom. We have a couple different configurations. So we commonly work with customers in these packaging challenges. And really from the start, when you're working with our solutions, it's not just a lab solution, but it's also going to be a fab ready and a production ready solution too. So if you have those challenges, myself and our engineering team, we have some dedicated engineers for photonics applications, and we can help with that. So give me a shout.
Thank you very much for that. When we talk about the sub-nanometer with 6 degrees of freedom alignment, I would like to ask back Luminar Freedom Photonics, Gordon Morrison. Do you have some challenges there on the accuracy that you need?
You're asking me about,
yes.
You're asking me about the accuracy that we need?
Yeah. Yes.
Yeah, by and large, with the alignment of our diode laser arrays, the accuracy of alignment has to be better than half a micron in order to have less than 3 dB coupling loss. And that's something we can achieve through brute force of butt coupling one component to another, and we've done that with arrays as well. What you run into as a problem, if you're talking about larger arrays of diodes, although they're lithographically defined in their position, and so consistent that in that sense, controlling the thickness of the bar across that length of several millimeters can become tricky when you're talking about less than half a micron. And then depending on whatever your bonding approach is for that bar, there's a certain amount of natural stress and strain that's going on. And so you tend to end up with a little bit of bowing or curving from one end to the other. And so if you've got two chips that don't have perfectly matching curves, it's not an easy problem to solve. This is something that I think a lot of different people are working on. You can solve it mechanically by careful design of the bar and design of the coupling optics, or you can try other brute force solutions such as photonic wire bonding, or I guess also this one-step lithography that Icon Photonics was also talking about.
I have many people in the room who would like to help you, who would like to assist you, and I would like to remind everyone at this step that after the meeting, I will make the one-by-one introductions by email so you all can contribute. And I believe that Jean-Luc has now the slide that he can share they can share with us. Jean-Luc? Jean-Luc
Right, indeed,
Icon?
I'm ready for that.
Yes.
So
this is a very important slide
it.
because I believe that many people here are going to be benefited by working with you on this.
Okay, so this is actually a slide which is showing you a main picture of the optical waveguides that we can do vertically. This is here the waveguide with a taper shape and some pillars to maintain it. But actually, this is just an illustration, and you can have to solution in more detail here, where you have actually the chip that is embedded on a silicon wafer approach, or this is your wafer if we are working at wafer level, on top of which you have the taper waveguide there, and you can see the same view there, or an optical microscopic view. It is made in polymer, so it's transparent over a wide range of wavelengths. So it's it can find applications from 600 nanometers to more than 2 micron. Wavelengths. Actually, we can go up to 5 micron. And then we can have mechanical fixture, for example, for your fiber attachment. That is an option. So you can also have the surface input-output array here, your chip and the structure we've seen here in an array of 12 or n times fibers. But you can find it as well, this structure, same, put on the edge of your chip and mechanically attached to it. So you can have the purpose of a mod size converter from your PIC to the fiber array. So finally, in terms of performances, you can find some examples here. If you want to couple to multimode fibers or to single mode fiber with the losses you can target. And well, today we're working for optical transceiver, but there is also the quantum computing, because with a mechanical fixture plus taper, you can, in the taper shape, compensate for the misalignment errors for the fiber to the chip. And then you can make it at room temperature, the alignment, in a blind mode, because you don't need an active alignment. You can be only passive. And then you cool it down to cryogenic temperature. And that is giving a high advantage for the quantum computing. And you can make it not for one device, but really collectively for arrays of tens of devices, if you'd like. So that was very short, just to put the focus on it.
But yes, now we got everyone, including Gordon, to understand, and Gordon understands now why I think there is a clear room for cooperation here. Gordon, I would like to only ask you that you have a follow-up discussion with only Jean-Luc and with all the others that I'm going to introduce to you, because with all these challenges, many people are already asking me to see they can have a discussion offline with you. It means the world that you were with us on this first online industry meeting. Thank you very much. And we're going to continue now with the program. We go from LiDAR to the world of pluggable transceivers, and we have one of the market leaders in the room. We had the company HG Genuine, the US subsidiary of HG Tech, represented today by Jim Theodoras, the VP from R&D from HG Genuine. Jim, thank you very much for being with us. The floor and the attention of everyone goes to you.
All right, thank you, Jose. Okay, I assume you can hear and see everything okay?
Yes.
So I'll be, as Jose mentioned, I'll be speaking from the perspective of an optical transceiver manufacturer. We were humming along pre-COVID around 23 to 24 million transceivers shipped a year. And this post-COVID boom really caught us and caught me by surprise. We're on track to ship 100 million transceivers this year. And I just bring that up to mention the scale of the problem we're dealing with when it comes to photonic testing and assembly. It's you know, I continue to learn. It's been a learning experience for me, and events like this are critical for bringing together the people to solve these kind of problems. So I won't go through this in detail in the interest of time, but suffice to say, no two transceivers are alike. You would think, being they look the same on the outside, maybe there's some commonality, but unfortunately today we still, all the packaging, assembly, and testing solutions are pretty custom to each variant. Now we do try to group together like things like DRs, FR4s, VCSEL-based, but in the end, it almost becomes a unique solution, a unique line for each of our transceivers. No two transceivers are alike. So I've shown this slide in the past, and I immediately was inundated with questions, people saying it was too complicated, I don't get it. So I'll spend a minute on this. So what I've plotted here is for one of our products. In red is our production volume from 0 to where we're at today, and then in blue is the cost coming down. And as you make more, the price comes down. That's everyone understands that basic economic theory. But there's different phases as we to the production cycle. So I call it the economic life cycles of a transceiver. And so at first there's the make it work, then there's the make it producible, and then there's what I call the make it profitable. And as an industry, I think to get out my soapbox here, I think we focus too much on the green and maybe the start of the yellow there. We are so focused on how do I make this work? How do I get to that next level? How do I get faster? That we forget most of the life cycle of the transceiver. So the majority of the transceiver revenue profits occur very late in this cycle. It's this blue region here. That's when you're really benefiting and profiting from all that hard work that came before it. And to put that into perspective, on a typical transceiver, we'll have 3 to 5 design engineers, 30 to 50 NPIEs, new product introduction engineers, and then 300 to 500 factory engineers. Those aren't the workers. Those are the engineers doing the machines, the jigs, the test fixtures, setting up the line, designing it. And that's almost unique per transceiver. So I've worked at companies before that were opposite of this, 300 to 500 design engineers, 30 to 50 NPIEs, and maybe 3 to 5 factory engineers helping set up a line. So I think as an industry, something we need to do better at is focusing on the blue where we actually are making the money. And again, that's why I love coming to these events, because it really gets the whole industry working on that blue section there, and helps us be more profitable. So I was asked to talk about what do I need from the people on this call, and this isn't techie and it probably isn't exotic, but it's the truth. Here's what I need. I need more cross-functional cooperation, which is why I make time for events like this. And today we've got, for instance, we've got this linear mentality where, you know, the wafer is focused on the best die they can make and delivering known good die, and then they throw it over the fence to the sub-assembly house or maybe the pick house, and they're focused on yields and and how good can I make that PIC meeting their spec? They throw it over the wall to me, the transceiver vendor. Now I'm focused on meeting MSA and IEEE specs. But really, we need each stage of this manufacturing process should contain assembly and test features needed by the other stages. And they can only do that at events like this, where we're all talking and collaborating to where they know what to put on there. So I'll just give one example of each of these. Just to help clarify what I'm referring to. For instance, the wafer, there was a, how to say it? So there was a wafer features that were being diced off, that I found were being diced off. I actually could use those at the next two stages. And so I asked the wafer manufacturer, stop throwing away your test coupons, and I need the bulk silicon as a mechanical handle. They weren't aware that that was a need. So simply communicating that, they were able to make that change. On the PIC, so the PIC designers are narrowly focused on how small can I make it, how many wafers can I, how many die can I get on a wafer? And maybe if you're doing a TSMC 5 nanometer part, that makes sense. But in some of these PIC wafer processes, maybe there's value added by not being focused on that. So I would argue, rather controversially, that it's okay to put throwaway assembly and test features on that PIC. For instance, if I can add 80 cents in electronics that are only used in manufacturing test, and then once it's in the field, they're never even powered up, and it saves me $8 in that blue area in manufacturing, it's worth it. And I was glad that Peter touched on the built-in self-test features that they put on, Cisco puts on their PICs. But I'd go one step further and say, if 80% of that die never got turned on in the field, but helped me in that blue phase, it'd be okay. So as long as you're not adding power, because I can power it down, as long as you're not affecting reliability, I don't care that PIC's twice the size. Again, if you save me $8 in assembly, but cost me 80 cents in parts, I'm willing to throw that away in the field. I don't care. And then maybe one example on the transceiver side is I already have microcontrollers and I already have A to Ds, D to As. So if I can add control loops that make the life of the PIC designer easier or the wafer designer easier, then that's worth it. That helps all of us. And one example, I had problems getting a certain part, and when I tracked it down, I said, "Oh, our wafer yields are really bad." And so then I worked with the wafer company. I said, "Why are the yields bad?" "Oh, we're missing this one corner." So there was one of the 9 corners they tested. One corner was being missed at the hot corner, and yet I was using the part with the text, so that didn't apply to me. And so I had another part number assigned and said, "Give me everything you've been failing." I never had an issue getting parts in again. So this communication really is a big thing. And so again, each stage in this process should have assembly and test features that the other guy needs, not just what you need to deliver your product. And I'm gonna move to this next one. So I added this weekend because I was asked to talk more about photonics packaging, assembly and testing, and what do we need. And so I am doing cool stuff like Peter at Cisco, but they're through several industry partners. I can't show their work. However, this is our internal Silicon Photonics team's work, so I can share this without worrying about NDAs. And so this is our, Peter showed his 400 gig DR4. That was through a 3D chiplet technology. This is our 2D Silicon Photonics thing. And so on this, for instance, we have 2 alignments. We have the free space alignment from the laser to the PIC through a mode coupler, but then we also have an FAU alignment that's done with the robot automatically. And so there's 2 FAU blocks that get aligned, both receiver and the transmitter. We also have sonogram inspection, X-ray inspection, and I've blocked out everything here, but those are clear elements because we have optical inspections as well. So that's an example of the type of stuff we do. I was also asked to talk about packaging. So what we saw PIC-wise in transceivers, 100, 200 gig tended to be wire bonded out. 400 gig, 800 gig tends to be flip chip, which Peter referred to. And then as we move to this OSFP XD, that's going to be 1.6 and 3.2 terabits, things will be moving to 3D chiplets. And all that means is it's flip chip, but you're stacking in the Z dimension vertically, chiplets on top of chiplets on top of chiplets. And so it's kind of flip chip extended to the 3D realm, and that will be needed. So, and then finally, Jose, Jan was, I think Jan will talk to this. Jan was asking, well, what if these common PPAP capabilities were available from an industrial base? Would you use them instead of internally? So the 2 top PIC companies currently globally, I would argue, is Intel and Cisco, and they have the benefit of having a lot of internal money. We were lucky in that we built a $100 million factory right before the boom, and so we have a lot of this equipment. But as an industry, I think what's holding us back, and I'm going to flip back to this blue part here, we need as an industrial capability to do this photonics packaging, assembling, and testing. So those companies, all those 100 companies focused on the green and the yellow, can turn to somebody for the blue and still make money. And I think we need to get away from having this internal vertical capability to where, as a whole, everyone here can go and get this stuff built. And then I think you'll see innovation and adoption of photonic PICs really take off. It's kind of narrowly used today, and what's holding us back is we don't have this common industry-wide PPAT capability, and that's what I have. And thank you again, Jose, for inviting me. This is a great to be a part of this industry-wide discussion on this topic.
It is the first of many, Jim. Get used to this, and you're also going to be one of our speakers
Awesome.
at our event in Silicon Valley on co-package and pluggable optics in cooperation with Cobo, hosted by DuPont Center, 26-27 of October. I can't wait for that meeting with such a great agenda and to find ways for us to work together. There are many people who have questions, many people who have comments, but I would like to bring to the room a foundry. We have global foundries in the room, and it's represented by Takako-san, Takako Hirokawa-san. Takako-san, good evening for you. Are you with us?
Yes, hello.
Hello, thank you very much for being with us, Takako. It is great to hear you. I just would like for you to say hello to everyone, but also to tell us what you do at Global Foundries and how you are addressing the need for wafer level packaging, wafer level testing, especially testing, and what brings you to this meeting.
Hi, yeah, so I work on the V-Groove at Global Foundries. So this is a technology that we developed with IBM a few years ago, and now we have V-grooves that we can manufacture on each chiplet. So yeah, we obviously people are very well aware of the challenges associated with testing in line, and yeah, so
on the V-Groove manufacturing, Takako, is there any challenge or room for cooperation that you could maybe see? Is there anything that you would think, oh my God, if I could find a company that could help me with this, that could be a great use of my time?
Yeah, I think right now, I guess broadly speaking, we have our manufacturing fibers at a certain pitch, but there is interest in making a tighter pitch, as well as there's also been some research on multi-core fibers as well. So how we end up packaging, if multi-core fibers end up being the direction we want to go in as an industry, how we package that is an interesting challenge, but we're not there yet.
Thank you
Jose,
so much. Yes, please, Jim, tell us.
Well, if I could comment, I've heard multiple times now reducing the pitch of the V-grooves, and that is so important. So I think the width of the transceivers hasn't gotten any wider, and so but the channel counts are going up. So we're now in a situation where when we move to 16 wide buses, that quarter micron spacing adds up to where it suddenly becomes too wide. And so, yes, moving that down and getting the fibers closer together is going to be very key to moving forward to the higher channel counts and transceivers, because they're not getting any wider. So our only choice is to get the fibers pitch reduced so we can fit more widthwise.
Yep.
We have more questions and comments. The next one is coming from IBM in Bromont, Canada. Alexander Janta. Alexander, good afternoon. Good afternoon for me. Good morning for you. Alexander? I lost Alexander. This is the problem of doing the meeting live. Alexander Yanta, 3, 2, 1. In the meantime, Jim and Takatko, I would like to introduce to a company that is very meaningful for our global industry network. The company is Heidelberg Instruments. Philip Paul, are you with us?
Yes, hello. Yes, I am.
So you have seen today from Takako that was talking about the gratings and the V groups and reducing the pitch between the V groups and the need for Jim on the coupling of the light. Philip, can you tell us what Heidelberg Instruments does, especially in the field of peak packaging? How can you help the companies around the table today?
Yes, so Heidelberg Instruments are specialists and world leader in maskless lithography. So we actually basically we're going in the direction that many packaging applications will need. That is that we want to dynamically align the basically make the lithography follow the wire bonding, or maybe even the flip chip bonding. So you might find that okay, we've seen some very impressive alignment of 200 nanometers earlier, but you always get some die shift, and Heidelberg Instruments is addressing this sort of from the other way up, that you bond down first, and with our lithography equipment, basically you'll be able to then match the physical location of wherever the bonds or wherever the structures are bonded. So it's kind of taking the reverse approach.
Thank you very much, Philip. Yes. Jim, there's many room for cooperation here. Many people want to get in touch with you. I just want to give you a teaser. There is a question from the YouTube. We are live streaming the event in YouTube. Many people are watching you right now, so I hope that you all look as good as you can and you all look fantastic. And the question is coming from Dr. Subhash Arya. His question is the following. Which modulation format is being used for the high data rate that you presented? Is it PAM4, PAM8, PAM16 format?
Well, so the industry was stuck at NRZ for a long time, and we made the leap around 100 gigabit Ethernet is when the leap was made to PAM4, because the bandwidths were outpacing the ability of the lasers to go faster. So the leap to PAM4 was made around 100 gigabit Ethernet. What comes after that, I can't really say, because the industry standards bodies are still working on, is it still PAM4? Does PAM6 make sense? Is there now, there's alternatives to PAM modulation are being discussed, but certainly everything was NRZ, then there was a leap to PAM4. What comes next? It's exciting. We'll see what the big brains of our industry come up with.
Jim, I can't wait to meet you at Silicon Valley at our event. We already have confirmation from keynote speakers from Meta and from Google. It's going to be quite a fantastic meeting. I can't wait to have dinner with you there with you. And we continue the meeting today. We go to our last speaker. It's 5:40 p.m. in the Netherlands, so it is exactly the time to go to our last speaker. And the last speaker requires no introduction, but I will try myself. We wanted to have the semiconductor approach, the semiconductor feeling in the peak packaging. And for that, we have Jan Bardalan, who has really huge experience from the semiconductor industry and who can help us make this very important bridge, which is key in the strategy of Optica for Photonics. Connect with Semicon. Jan, thank you very much for being with us. The floor and the attention of everyone. What a beautiful room, right, Jan? The floor and the attention of everyone goes to you.
Thank you. Let me talk to you a little bit. First of all, I want to thank you for inviting me. And I want to talk to you a little bit about what we see are the challenges. And I'm glad that you placed me kind of at the end of the discussion, because I think that we have really seen a lot today. And one of the first things that I want to mention is that in our challenges that we see, and this is really kind of what we want to talk about, is that the main challenges that we have seen are, it's not like they're totally technically insurmountable. And I think that's what our discussion has shown us today. But really integrating things are the issue. And I think we need to work more on our ecosystem. I think that's been pointed out today, including design capabilities. We really haven't talked enough about design. First of all, there's no standard PDK for the silicon fab simulations or assembly. Everybody has their own process. Our light source is really a long and expensive development cycle. We're going to have more co-design of the ASIC and the silicon photonics, especially, and I'm really talking about co-packaged optics. There's really not any standardization of our module assembly, including the fiber light source attach and test. And every product has this kind of custom assembly infrastructure and process. And if we want to lower our cost, we have to have less customization and more standardization. And so really what we need is we need the readily available standard components that can be integrated by our OSATs and our OEMs. So we very easily need to be able to test and debug. We have to have a low-cost assembly process to get ourselves to the high volume, including the fiber attach. And that brings me to one of the things that we've been talking to people about. People have told us that one of the greatest challenges in the co-packaged optics is the fiber attach, how to attach it, whether we use epoxy or solder, and there's a lot of people exploring new methods. Also, another area is integrating the lasers in the package. If we integrate the laser in the package on chip, it's going to give us the lowest form factor, lowest power, lowest cost, better testability, and easier to repair. But the temperatures, if we put it on the chip, could degrade. We have to figure out how to replace the lasers. We were also talking in co-packaged optics about moving from the pluggable formats, which we are also familiar with, they're in very high volume today, to mounting something like a BGA either on the board or as a socketed solution. And as we approach that, we need to be able to figure out how to replace that, to upgrade, to do field repair. And we have to have some standards to lower the cost and the manufacturing cycle time. So I think that we have a lot of things that we're seeing done today, but we have to continue to work together. And an opportunity like this is fantastic. So thank you very much.
Thank you very much, Jan. How could you advise us, the Optica industry team, to interact closer with the semiconductor companies? Many of the semiconductor companies in the US are really photonic companies, like, for example, Intel. And today we have global foundries in the room, but we would like to bring more semiconductor players.
Well,
how can we convince them to be part of these chip acts that are going on in the US and Europe?
I know that TSMC is doing a lot of work in this area. They've published things. We need to have them come into this forum as well, because a lot of people have their component, their devices fabricated there. We need to have our assembly partners, Amkor, ASE, in this discussion. And we need to have more of these forums where we talk about these things. We also need to have some more of the design community in as well to talk to us about some of the challenges. So I think that by combining all these parts of the ecosystem, including the equipment and materials people, we can really move ahead in this area quite rapidly.
When it comes to the design, and when it comes to also to the design and test, because very often they go together. There is a company that has been really setting up the stone for the supply chain. The company was acquired by Hitachi 2 years ago. It's in Valencia, and I'm talking, of course, about VLC Photonics. Paulius Naujalis, thank you very much for being with us today. There are many companies in the room who are already your customers, many companies who are also your suppliers. Could you tell us a bit what are your current situation when it comes to offering to your customers not only design, but also testing, and how do you do that? Paulius, we cannot hear you, and we really, really want to.
Oh,
Can you?
sorry.
Yes.
Apologies for that.
Yes.
So yeah, we are here in VLC Photonics in Valencia. We're actually doing more and more work towards characterization packaging as well. And we start to use wafer level tools and for wafers as well, and for single chips as well, using conventional methods by using manual characterization tools and automated as well. We closely collaborate here with a company who is as well attending in here, Icon-Tech, so to develop the tooling for all kinds of assemblies and automated testing. And we start offering these services as well for external users and all the people around here who's meeting us here today.
You have started offering packaging services to your customers, and that is based on automation. In the presentation in the beginning by Peter, he actually talked about the testing and characterization and the need to often do very deep testing for many of the structure, even including bit error rates. What kind of testing are you supplying to your customer? Is mostly the IV, or do you provide in-depth testing at wafer level or at die level?
Indeed, we provide both die level and wafer level testing services right now, and we're getting better on tooling. So now we start to offer as well for transceivers some high-speed characterization, system level characterization as well, not only the single component testing. So we just acquired tools for up to 110G modulation characterization. So for transceivers and high-speed applications, we can easily support a lot of people around here, both on wafer level and single die as well.
Peter the doubler, let me come back to you from the beginning to close the circle nicely. In the beginning of the presentation, where you talked about testing, you were talking about the need to the bit error rate testing, the BER testing for some of your structures. As a customer of Foundries, Luxtern was always a fabless company in the origin. What is currently, in your opinion, the need for testing of the chips when it comes out of the foundry? How close are we from the semiconductor approach that Jan Vardalan is used to, that you don't really need to test the chips when they arrive from the foundry?
Oh, you always have to test. Everyone is testing the chips when they come from the foundry. But you look at the test flow, the foundry, before they can ship wafers to us, and that's general for electronic and photonic wafers, they do what's called the wafer acceptance test. They test some structures on the wafer, and based on the test results, they decide that they can ship the wafer to us or not. And we have to accept the wafers when they pass the wafer acceptance test. So these are like kind of crude tests. But after that, you own the wafer, and then you have to test every chip that you have designed. That is, of course, your design is your responsibility. So that if there's yield fallout there, then you have to deal with it. And that testing is usually done with both for photonic wafers, optically and electrically. And there are certain test structures we have to test if that is okay, if these chips are okay. And then when you go to the next step, you assemble a chipset, then you can test that bit error rate test and all of that that I just mentioned using the built-in self-test. If you cannot do built-in self-test, for instance, if you have TX and RX separately, then you have to try to test these things independently. You probably need more high-speed test equipment, which is more expensive and slower, or you take the yield hit at the end, which is not preferred when you test at speed at the module level, but then your yields need to be very high, or you throw away a lot of modules. So that's the flow.
Let's hear the point of view, because you present the point of view as the customer of the foundry. Let's hear the point of view of the foundry. We have one of the silicon nitride foundries that has set up the pace of manufacturing silicon nitride in the world, coming all the way from Lausanne, but now setting up offices worldwide and collaborating with semiconductor foundries. And talking, of course, about Ligentech. Davide Balzanella, thank you so much. Grazie mille for being with us today. Davide, you just heard the perspective of Peter the Doubler about the testing that is needed as a customer of the foundry. Could you tell us, as a foundry, what testing you provide? And if you could you tell us a couple of challenges that the rest of the companies today could help you with?
Well, thank you, first of all, for having me here. Let me start by saying that I just joined Ligentech a few months ago, so I'm quite new of the of the whole business. But I work here as a test engineer, and certainly what we want to do is to establish a very, let's say, pipeline for the testing from from our foundries to what we can actually ship to the customer. So we want to have to create a pipeline that we can understand. We know that it's reliable, and we want to test everything we can, of course. But it's always difficult to understand which are the most important part that we have to focus on.
Thomas Hessler from Ligentech. It is so great to have you here. Thomas Hessler is the CEO of Ligentech. Davide gave a good perspective, but I would like Thomas to tell us about what kind of cooperations. We are very amazed by your cooperation with XFAB last year. What kind of other cooperations did you looking to bring the silicon nitride photonic platform to the semiconductor mindset?
And a proud Optica member. Thanks, Jose. Since a long time. Well, first of all, maybe to go a little bit back to the first question, I think one of the key challenges to link the PCM measurement for wafer acceptance to the yield of the customer device. To make that strong link, that's one of the key challenges, to have that loop closed. What kind of collaboration? I mean, I think that is quite was a big step with XFAB, and in terms of mindset, I think it starts with the people. So we have quite well, one of our founders. He comes from the semiconductor industry, and I think that where the majority of that mindset is started. So it's really think industrial. I have a lot of industrial experience in that area. I think it's really not to come from the academic viewpoint, but having seen it in industry. I don't want to talk too much about upcoming collaborations at the moment, please understand.
I am very well. The one from XFAB is public, and I would like to congratulate you because that really has been a stepping stone for all the efforts that the photonic companies are doing in Europe and US connecting with semiconductor companies. So thank you very much for that, Thomas. I cannot finish a meeting on photonic packaging without giving the floor to PhyContech. I cannot. I have Moritz in the room. Moritz, thank you very much for being with us today. I would like for you heard about the needs from companies like HETech, like Luminar, like the Global Foundries, Cisco. Could you tell us a couple of follow-ups, a couple of interesting mindsets that are now in your mind after the last 2 hours?
Yes, so first of all, thank you, Jose, and it's nice to see you with the same energy and motivation in your new role. So it's good that you're saying the same person. So I actually need to admit that I could not follow all the complete discussion, so I may have missed a few points here and there. But what's quite interesting for us, and I think it's the general photonic trend, is there's so much going on also in different aspects of the photonics world. So there's wherever we are looking, there's so many new opportunities, new challenges. But it's good to see that there's so many great people working on that. So and so from our side, it's really fascinating to see where all of this is driving in the future. And we were happy being a part of that photonic community. And the challenges we are seeing is quite nice. So for us, this is, I mean, you know exactly what we're doing. So it's photonics assembly and testing. And for us, some of the trends is really the higher degree of automation, which is for sure there since a lot of years, but we are seeing now with the line concepts we are pushing quite a good step into industrial
Moritz, one of the highlights for me today was the presentation from Gordon Morrison when he presented how they are using the machine from Vanguard Photonics to do the two-photon polymerization and the photonic wire bonds. And that is an automated machine that was done in cooperation with PhyContech. And on that, there was a success story of an introduction made in the past. And I would like to remind all of you what I want to say with this. Introductions really drive this business. If you want to get in touch, beautiful t-shirt, Mark Lukovic. If you want to get in touch with any of the participants today, all you have to do is send me an email. We're going to share with you in advance all the participant lists in the coming meetings. For this one, after the summer holidays, so many people registered on the last day that we didn't want to share it without having complete. In the next one, you're going to have it in advance. This one, you're going to have one day after the meeting, 490 people registered. You're going to have the people, the name and LinkedIn addresses, not the emails, of course. If you want to get in touch with any of them, all you have to do is send me an email and we'll make the introduction. We do this for the cooperation. Let me just remind in 30 seconds, we talk from Cisco and they share with us their needs for packaging and test for some of the key driven factors from the Luxtera point of view. It was great to have Peter the Doubler. We talked from DARPA about the key initiatives and we focus on the MOAF, Gryphon, pipes, those and the chips 3D integration. Then afterwards, we have Freedom Photonics, a luminar company with perhaps the highlight of the event, their key challenges, the key room for cooperation in the packaging of FNCW LiDAR modules, and we also have HG Genuine that we're looking for partnership and cooperation for continuing their trend on their pluggable package transceivers. This has been a fantastic meeting. For all of you who want to have a follow-up discussion, stay on. For those of you following the meeting in YouTube, we're going to finish the live stream now. You're going to miss the rest of the meeting. Thank you very much, everyone. Thank you for making the first online industry meeting of Optica a very, very special one.